Over 2 billion years ago, Earth nearly lost the very oxygen that made complex life possible. During the Proterozoic Crises, the planet's atmosphere faltered, and survival hung by a thread. How close did life come to disappearing forever? If you enjoy exploring these ancient mysteries, please like, subscribe and share, and tell us in the comments. Do you think life could have recovered if oxygen had vanished completely? Thank you for watching. Now let's begin. The planet turns under a pale sun, its continents worn low by long erosion, its seas wide and shallow. The time lies not far beyond the first great rise of oxygen, an interval when a world seems to have steadied after chaos. In the wake of volcanic violence and bacterial conquest, the air holds new gases it has never known before. Oxygen, once a trace within a methane haze, now drifts into the upper sky and meets ultraviolet light, forming a thin shield of ozone that softens radiation and tints the horizon faint blue. For the first time, the air carries the faint scent of oxidation rocks rusting, minerals changing metals, losing their shine. Iron, once kept soluble in the anoxic seas, now falls as red sediment to the seafloor, painting layers that future stone will remember. Across vast shelves, carbonate platforms grow under sunlight that penetrates clear water. The early oxygenation has altered nearly every boundary the crust breathes. The oceans shimmer differently, and the sky itself takes on a gentler tone. Yet beneath the calm surface, slow changes begin that will eventually undo much of this new order. The chemistry of the planet adjusts in ways invisible but profound. Oxygen reacts quickly. Every atom finds something to bind with hydrogen, carbon, sulfur, or iron. For a time, production by photosynthetic microbes outpaces its loss. The shallow seas, bright with cyanobacterial mats, supply oxygen that diffuses upward into air and downward into sediment. In those upper layers, complex microbial communities thrive, using the new oxidant to draw energy from organic matter. But deeper down, beyond the reach of light, oxygen vanishes. The transition between oxygenated and anoxic zones is sharp, sometimes only a few centimeters thick. Beneath it, life continues in its older ways, using sulfate carbon dioxide or iron as electron acceptors. The planet becomes layered with thin skins of oxygen stability, lying over vast domains untouched by it. In the early aftermath of this change, the carbon cycle swings toward imbalance. Organic matter burial increases as productivity rises in surface waters. Carbon isotopes record this shift, showing a long interval of positive values, evidence that much carbon is being stored away in sediments, rather than returned to the atmosphere as carbon dioxide. The climate stabilizes, glaciers retreat, weathering on continents accelerates under an oxidizing atmosphere, releasing more nutrients to the ocean. It seems as though Earth has found equilibrium after billions of years of volatility. Yet the balance depends on a fragile partnership between biology and geology, one that will not last forever. Across the continent, soils deepen. Oxygen combines with metals in rocks, forming oxides that redden the land and trap once mobile elements. Rivers carry these products to the ocean, enriching coastal zones, but also removing reactive metals from circulation. The iron that once fed early photosynthesizers now precipitates before reaching the open sea. Productivity shifts. Some microbial communities flourish, others decline. Slowly, the supply of key nutrients dwindles. In the open ocean, far from shore, life begins to feel the shortage. Photosynthetic organisms that depend on iron and phosphorus struggle to sustain oxygen release. The atmosphere, once climbing in oxygen content, starts to plateau. Then gradually it drifts downward. The decline is slow, measured in tens of millions of years. It is not felt as catastrophe, but as gradual suffocation of possibility. The surface air remains breathable for microbes, but thin for anything more demanding. Fires which require abundant oxygen cannot yet sustain themselves widely. Lightning still flashes, but most strikes fade into smoke rather than flame. With each passing epoch, the reddish soils darken again, as reduced compounds accumulate. The planet enters a long, quiet phase, a transition not of extinction but of dormancy. In the seas, the shift is more immediate. As oxygen diminishes, deep waters regain their former chemistry. Iron, once oxidized and settled, dissolves again under reducing conditions. Manganese follows. The oceans darken from blue to green to brownish grey. Hydrogen sulfide produced by sulfate-reducing bacteria in sediments begins to leak upward into mid-depths. At first, these zones remain localized bound to restricted basins, but over time they spread. The chemical gradient between oxygenated and anoxic waters becomes unstable, its boundary oscillating with climate and circulation. Some shallow platforms remain bright with oxygenic life, while others slip back into dim sulfidic states. The transformation is uneven but relentless. The atmosphere reflects this slow retreat. The proportion of oxygen may now be no more than a few parts per hundred compared to the present world. Yet the planet remains stable enough to avoid collapse into the methane haze that once smothered it. Methane concentrations stay low, constrained by residual oxygen. The result is a world half changed, neither truly oxidized nor fully reduced. Skies are pale clouds, thin light diffuse. It is an Earth holding its breath, balanced between two states. At the surface, stromatolites still rise as layered domes of microbial sediment, but their abundance begins to wane. Many shallow settings become inhospitable as sulfide intrudes upward. Communities retreat to refuges where currents bring renewed oxygen. The organisms that once flourished everywhere now cluster in patches, surviving within narrow environmental tolerances. Beneath their mats, chemical gradients sharpen, further forcing evolution of metabolic diversity. Microbes capable of switching between oxygen and sulfate respiration find advantage. Others rely on nitrates or iron oxides as alternative electron acceptors. In this quiet struggle, the foundations of later complexity are being laid, though the process remains slow and without witness. Over geological time, these interactions between life and environment feed back into the carbon cycle. The burial of organic matter slows as oxygen availability declines. Carbon dioxide levels creep upward, warming the planet slightly. The ocean's capacity to absorb carbon weakens and volcanic outgassing adds to the load. Still, without large continents covered by vegetation, the cycle remains moderated. Earth drifts through a long, mild climate punctuated by subtle oscillations in temperature and sea level. The appearance of stability conceals deep chemical reorganization. Each atom of oxygen produced by photosynthesis must find a sink, a molecule to oxidize a mineral, to alter an isotope, to fix. As these sinks fill and empty, the atmosphere responds. When volcanic gases rise rich in sulfur and carbon, they consume oxygen. When burial rates increase, oxygen accumulates. The two processes balance delicately, producing the long rhythmic pattern recorded in isotope ratios. These signatures, later measured in carbonate rocks and organic shales, will reveal to scientists that the Earth's early oxygenation was not a single event, but a pulse that rose and faded. Toward the end of this first stable phase, the land is quiet. No plants yet break the surface, no animals yet stir. Only microbial mats cling to damp soils and tidal flats, darkening and drying in the sun. The air above them holds a faint trace of ozone that filters sunlight, allowing surface waters to remain relatively calm. Each dawn repeats the same pattern. Photosynthetic blooms in shallow pools release oxygen that bubbles briefly into air, while beneath them reducing reactions consume it again. The cycle continues patient and self-cancelling. What began as a planetary revolution now slows into equilibrium, an uneasy calm between oxidation and reduction, life and geology. From orbit, if one could observe, Earth would appear serene. The continents are broad and subdued margins fringed with carbonate reefs. The ocean colour shifts subtly from turquoise to deeper green where sulfide builds up. Clouds drift thinly untroubled by storms. Yet within that calm, the chemistry of survival is shifting towards scarcity. The first breath of planetary oxygen is becoming a sigh. The stage is set for the long, low oxygen age to come, a time when the atmosphere remains faint and the oceans turn shadowed once more. The world enters a period of extended calm. After the turbulence of the early oxygen rise, the Proterozoic Earth drifts into stability that seems endless. Continental shapes change, little erosion rounds mountains and shallow seas spread over low-lying platforms. In the oceans, an air-chemical balances reach a near steady state, one that holds for tens of millions of years. Carbon isotope values remain high, marking a time when burial of organic matter outpaces its return to the atmosphere. This prolonged interval of positive carbon signatures, the shadow of the Lomagundi-Getuli event, reflects the planet's attempt to sustain the oxygenation it briefly achieved. Rocks formed in these ages preserve thick carbonate layers built by microbial communities thriving in well-lit shallows. Yet beneath the smooth surface of geochemical order lies an emerging quiet decline. The same processes that once fostered oxygen abundance now begin to exhaust their potential. On land, oxidative weathering continues. Exposed rocks react with air drawing oxygen from the atmosphere to form stable oxides and releasing elements into rivers. The pace is slow but persistent. The vastness of exposed continental crust during the early Proterozoic makes the oxygen sink immense. Every grain of reduced mineral presents a surface where oxygen is consumed. At first, biological production in the oceans compensates for this loss. Cyanobacteria remain widespread coating sediments and floating in coastal waters, fixing carbon and releasing oxygen as before. But the easy sources of nutrients, phosphorus, iron, molybdenum, become less available as they bind to newly formed oxides or wash into the deep ocean where oxygen cannot reach. Productivity declines without drama. The balance tips gently away from abundance. The skies remain pale sunlight, diffused through a thin ozone layer that filters harsh, ultraviolet radiation. Without dense oxygen, the atmospheric pressure differs from modern air. Perhaps cooler overall, it carries less of the reactive chemistry that today shapes weather and lightning. Clouds form low and dissipate slowly. Rains are soft and infrequent. The absence of plants means landscapes are bare weathering controlled by chemical reaction rather than roots. Rivers move through wide channels filled with silt and iron oxides, their slow flow feeding coastal deltas where microbial mats continue their patient work. Each tide lifts and lowers layers of sediment, trapping bubbles of oxygen that vanish within hours as bacteria consume them. The oceans hold the key to this long equilibrium. Above the thermocline, the water stays mildly oxygenated enough for photosynthetic and heterotrophic microbes to coexist. Below it, the deep ocean remains largely anoxic. Iron once fixed as oxide minerals begins to dissolve again, forming iron-rich layers that drift upward with currents. When these waters encounter oxygen near the surface, iron oxidizes and falls a constant rain of fine particles that record redox shifts in alternating bands. This slow vertical exchange defines the mid-Proterozoic sea oxygen at the top, anoxia below chemical gradients holding steady. The planet seems asleep, breathing shallowly but evenly. Such stasis affects every cycle. carbon burial continues but with gradually diminishing strength. The ratio of organic to inorganic carbon in sediments shifts, signaling that less new organic matter is being produced. Sulfur isotopes also stabilize, reflecting limited large-scale volcanism and weathering flux. The planet's interior remains active but subdued. Supercontinents assemble and break apart at glacial pace. Magmatic gases still vent through rifts and subduction zones, providing a minor counterbalance to surface oxidation. Yet even these emissions become part of the quiet rhythm. Nothing in this age proceeds quickly. Geochemical flux is slow, biological innovation pauses, and climate remains mild. This drawn-out stability is both remarkable and deceptive. It marks one of the longest steady states in Earth's history, hundreds of millions of years, when oxygen levels, carbon cycling, and climate vary only within narrow bounds. To later observers, this will appear as the boring billion, but in its own time it is an age of subtle transformation. In the absence of upheaval, slow reactions reshape the crust and oceans molecule by molecule. Iron formation patterns change, manganese nodules accumulate, organic shales build thick sequences. These quiet processes reset the redox potential of the Earth system, preparing conditions for future instability. In the shallows, microbial life adapts to gradual change. Cyanobacterial mats thicken during long periods of calm and retreat when nutrient scarcity deepens. Stromatolites-layered sedimentary structures built by these organisms remain common but grow slowly. Their internal laminae preserve rhythmic cycles of sedimentation, capturing seasonal variations in light temperature and oxygen. The record shows no sharp transitions, only an endless repetition of similar conditions. Even so, subtle genetic diversification continues beneath this uniform appearance. Microbial lineages explore metabolic flexibility, experimenting with nitrogen fixation and metal reduction to survive in nutrient-poor settings. These hidden adaptations will later shape the course of evolution when oxygen rises again. As the carbon cycle balances on the edge of neutrality, the isotopic signal begins to drift. The long positive excursion that once reflected high organic burial gradually wanes. Carbon isotopes slide toward baseline, implying that oxidation of buried carbon is catching up with production. Some of this oxidation happens in subsurface sediments, where oxygen diffuses downward and reacts with ancient organic matter. Some occurs on land as eroded shales expose carbon-rich layers to air. The overall effect is a slow bleed of oxygen from the atmosphere, a process unnoticed by any living creature but relentless in scale. In these conditions, the ocean's chemistry becomes increasingly sensitive to small disturbances. Slight changes in nutrient supply or circulation can flip local basins between oxygenated and sulfidic states. Hydrogen sulfide produced by sulfate-reducing bacteria begins to accumulate in restricted regions. This is not yet the full expansion of Euxinia, but the first whisper of its return. Sediments in these settings preserve pyrite and distinctive sulfur isotope fractionations that tell of partial oxidation and reduction cycles. Where oxygen still lingers, it forms a thin layer only meters thick. The rest of the water column remains under chemical control of microbes rather than atmospheric exchange. Climate mirrors the planet's composure. With volcanic outgassing moderate and weathering efficient carbon dioxide levels hold steady enough to maintain temperate conditions. No ice sheets extend across the continents and no runaway greenhouse develops. The sun, fainter than today, shines through an atmosphere thin yet adequate to preserve warmth. Days are long, the rotation of Earth slightly slower than in the Archean, and tides remain strong in shallow seas. Each environmental parameter finds its equilibrium. The world has entered a geological pause between revolutions. From orbit, if seen in this age, Earth would appear muted. Its continents carry the dull reds and greys of iron oxides. The oceans gleam olive where microbial films spread across the surface. The faint blue cast of the sky is softened by haze less vibrant than before. There are no forests or deserts, no polar ice caps, only the slow breathing of a stable planet. To human eyes it might seem uneventful, but to chemistry it is an era of vast but hidden transaction. Oxygen traded for rock-bound elements, carbon exchanged between air and sea life confined within narrow chemical margins. Toward the end of this interval, hints of imbalance begin to return. The long-standing positive carbon isotope plateau starts to waver, suggesting that the engines of oxygen production and burial are faltering. Weathering on land, though steady, can no longer supply the nutrients required to sustain marine productivity. Deep ocean mixing slows perhaps as continental arrangements alter currents. Anoxia creeps upward in certain basins. Still, the shift is so gradual that no single generation of microbes notices it. The Earth remains mostly serene, unaware of its slow drift toward depletion. The great oxygenation that once transformed the planet has entered remission, and the quiet world now stands at the threshold of decline. The stillness of the mid-Proterozoic world conceals a subtle transformation taking place beneath the surface of the seas. For millions of years, the upper ocean has remained faintly oxygenated, its shallow platforms rich in carbonate sediments and microbial mats. Yet below this thin layer of stability, the chemistry of the deep ocean is changing. Iron, once bound as insoluble oxides in oxygenated water, begins to return to solution. As oxygen supply dwindles, redox boundaries shift upward through the water column, allowing the metals once buried in the sediment to rise again. These changes unfold slowly and visible to the surface, but they mark the beginning of a new phase in Earth's long oxygen struggle. The same elements that had been locked away after the Great Oxidation now dissolve back into circulation, darkening the sea and reminding the planet of its ancient chemistry. Within the deep basins, water no longer receives enough oxygen from above to maintain oxidized conditions. Microbial respiration consumes what little diffuses downward, leaving the abyssal layers rich in reduced species. Ferrous iron released from sediments moves upward with sluggish currents. Manganese follows along with traces of nickel and cobalt. In the absence of oxygen, these metals remain soluble, drifting silently through the dark. Where the layers of rising reduced water meet the overlying oxygenated zone, a narrow boundary forms glowing faintly with suspended iron oxides that precipitate out when they encounter oxygen. This transition zone becomes a realm of constant chemical tension, a thin sheet of reaction separating two ancient worlds. Above it, life continues as before. Below, the ocean reverts to a state last common billions of years earlier. The reappearance of dissolved iron reshapes the ocean's appearance. The once green surface waters take on brownish hues and their transparency declines. Sunlight penetrates less deeply, limiting photosynthesis to shallower depths. Cyanobacteria dependent on light become concentrated near the surface. Below them, microbial communities adapted to dim conditions expand, including those capable of anoxygenic photosynthesis, using ferrous iron as an electron donor. These organisms thrive where the redox boundary rises into the photic zone, forming bands of rusty plankton that bloom when currents stir deeper water upward. Each pulse of mixing paints new layers of iron-rich sediment, recording in stone the slow breathing of the ocean. The metals themselves influence biology in complex ways. Many serve as cofactors in enzymes essential for life. In small amounts they enhance metabolism, but in excess they become toxic. The balance is delicate, and as iron concentrations climb, some microbial lineages struggle. Others adapt evolving mechanisms to regulate internal chemistry, or to precipitate protective minerals around their cells. The interplay between toxicity and necessity shapes the diversity of life in these iron-dominated seas. Over time, the availability of certain trace metals fluctuates dramatically. Molybdenum and copper, both required for enzymes involved in oxygen use, become scarce because they precipitate under sulfidic conditions. This shortage further restricts oxygenic photosynthesis and reinforces the planet's decline into low-oxygen states. Geologists will one day read this history in banded iron formations that reappear sporadically after a long absence. Though not as massive as those of the Archean, these younger deposits tell of renewed contact between reduced and oxidized waters. Their presence signals that oxygen production still persists, but only in localized zones. The global balance has tilted back toward reduction. Where once vast quantities of oxygen accumulated in the air, now it is largely consumed in the oxidation of metals and sulfur within the oceans. The result is a world again ruled by chemistry rather than atmosphere, a place where every molecule of oxygen finds a sink before reaching the upper sky. On land, the same process unfolds more subtly. Weathering under a weakening oxidant changes the composition of soils and sediments. Iron that had formed bright red oxides darkens as it converts to reduced minerals. Drainage waters carry dissolved metals toward the coast, enriching estuaries and marginal basins. These environments become hotbeds of microbial cycling, where oxidation and reduction alternate over daily and seasonal rhythms. As tides expose sediments to air and then submerge them again, thin crusts of oxide form and break, perpetuating local oxygen consumption. The atmosphere above these regions remains in tenuous equilibrium, sustained by a balance between oxygen production in open seas and its destruction along every interface with rock and water. At the scale of the whole planet, the geochemical loops tighten. The deep ocean stores vast reservoirs of reduced species acting as an oxygen sink that grows with time. Occasional overturning events bring this water to the surface, triggering bursts of oxidation that briefly raise atmospheric oxygen levels. Yet each surge is followed by renewed decline as the freshly oxidized metals sink once more. This seesaw pattern is recorded in subtle isotopic oscillations within carbonate rocks and shales. Carbon isotope ratios reflect alternating periods of organic carbon burial and oxidation, while sulfur isotopes trace the balance between sulfate and sulfide. The rock record thus becomes a slow-moving echo of the planet's respiratory rhythm. In this world of iron-laden seas, the colour of light shifts. The scattering of suspended particles gives the ocean a darker tone, reducing reflection and slightly altering climate feedbacks. Less light penetration means cooler surface waters, which suppress evaporation and weaken rainfall on land. Drier continents in turn reduce weathering rates, slowing the delivery of nutrients to the sea. The system closes upon itself. Fewer nutrients mean less biological oxygen production, which allows more iron to remain dissolved. The planet's cycles now reinforce depletion rather than renewal. What began as a subtle geochemical shift has become a self-stabilizing condition of scarcity. Life persists but changes character. In coastal lagoons and restricted basins, purple and green sulfur bacteria form dense mats, feeding on hydrogen sulfide that seeps upward from the sediments. Their pigments colour the water with soft violet and olive tones, absorbing wavelengths unused by cyanobacteria. Above them, thin films of oxygenic microbes survive, separating the toxic depth from the open air. The layered structure of these communities mirrors the chemical stratification of the ocean itself, oxygen on top sulfide below, and iron cycling between. The boundaries between these worlds are narrow yet immensely productive, driving the slow exchange of energy that maintains the biosphere through the Proterozoic calm. The presence of dissolved metals also affects the burial of organic matter. Iron bind with sulfur to form pyrite, a stable mineral that traps reduced sulfur permanently in sediments. Each grain of pyrite represents a tiny transfer of oxygen to the atmosphere, because forming it consumes reduced material that would otherwise react with oxygen. Paradoxically, the very processes that darken the oceans contribute small increments of oxygen stability, but the scale is too small to reverse the trend. The planet's budget remains dominated by sinks. Oxygen levels hover low, perhaps near 1% of modern values, never collapsing completely but never recovering. As ages pass, continents shift slowly, carrying with them basins where metal-rich sediments accumulate. These deposits, once buried, become part of the geological archive that will later feed industrial civilizations. But for now, they are silent witnesses to an atmosphere caught in long suspense. Each wave that laps against an iron-stained shore releases the faint smell of sulfide. Each river mouth delivers more reduced matter to the sea. The earth glows faintly red-brown from space, its color, a reflection of chemical restraint. By the close of this era, the return of dissolved metals is complete. The oceans have settled into a quasi-permanent stratification, oxygen near the surface, iron and sulfide below. The contrast defines the next hundreds of millions of years. The early optimism of planetary oxygenation has given way to equilibrium ruled by minerals and microbes. Beneath the still skies, the slow reaction between oxygen and metal continues, a quiet contest that neither side can win. The stage is set for the next descent when the air thins further and the seas turn from merely dark to truly sulfidic. The air thins into a quieter composition, holding oxygen at a small fraction of the modern level, while the sky keeps a pale cast. Ozone remains, but as a modest shield enough to blunt the harshest radiation, yet not strong enough to deepen the blue. Sunlight arrives softly, passing through a column of gases that has grown less reactive with oxygen, and more patient with trace species. Winds move dry and unhurried over low continents, their surfaces washed in iron oxides and clays. Dust rises from bare ground and settles into the sea, adding small cargoes of phosphorus and metals that drift downward through the upper water. The planet breathes with long, shallow cycles, the atmosphere exchanging slowly with the ocean below, the two systems joined by the daily work of microbes that feed on light carbon and the redox differences that remain. In this world, oxygen exists but does not dominate. It skims the surface as a thin lens, a workable oxidant in shallow waters, and tidal flats a rare presence in the open air where fires seldom take hold. Lightning still forks through summer clouds, but ignitions fade quickly without enough oxygen to sustain flame. The land bears no charred horizons. The geologic memory of fire is still minimal. Across the surface ocean, the chemistry fits the air above it. The uppermost waters are mildly oxygenated, especially where wind and waves mix them with the thin atmosphere. Here, during daylight, photosynthetic microbes produce oxygen that saturates local layers for hours. At dusk, the oxygen falls as respiration and chemical reactions consume what was made. Night after night, the pattern repeats, a slight surplus by day, a near deficit by dawn. Below this rhythmic skin, the anoxic depths resume, holding ferrous iron and hydrogen sulfide carried upward by slow diffusion and weak overturning. Where these reduced species brush the base of the oxygenated layer, thin reaction zones form, turning dissolved iron into fine particles that settle through the twilight. From above, the sea appears calm. From within it, sharp chemical fronts fold and drift like slow-motion weather in a planet of water. The atmosphere carries signals of this balance. With oxygen, low methane remains constrained but not absent. Residual oxidation in air and water keeps it modest. Nitrous oxide forms in pockets where oxygen is scarce yet not entirely gone, another reflection of microbial pathways that thrive in intermediate conditions. The ozone column, drawn from sparse oxygen, still filters the hardest ultraviolet bands, permitting life to work near the surface without constant damage. Yet the colours of the day are subdued. At noon the sky is washed and pale. At sunrise and sunset the light spreads in long bands, because aerosols and thin haze scatter the red and yellow tones across the horizon. The physics of the air aligns with its chemistry, fewer oxidants to scrub particles gentler, conversion of gases, longer residence times for the substances that trace biological and volcanic breathing. On the continents, weathering proceeds under this faint oxidant. Iron in minerals changes state more slowly, and soils evolve without roots to open pores or trap nutrients. Rainwater picks up carbon dioxide from the air, forms weak acid, and reacts with rocks to release ions that rivers carry to the sea. The pace is steady rather than strong. Each drop of water that touches the land removes a minute fraction of reduced elements, and each atom of oxygen that meets those elements disappears from the air. Over long intervals, the ledger stays near balance, neither allowing oxygen to build nor inviting it to collapse. The quiet is not a pause in reaction, but a saturation of slow processes that match one another. Within shallow coastal settings, the atmosphere leaves delicate fingerprints. In tidal flats, daily oxygen pulses reach the matte surfaces, driving a thin band of oxidative chemistry, before the tide recedes and sulfide rises again. In lagoons partly cut off from the sea, calm air limits mixing, and the water column stratifies. The upper layer borrows oxygen from wind and light. The lower layer draws on sulfate and iron to fuel microbial respiration. Between these layers, the boundary migrates with seasons, with storms, and with small shifts in river input. The air above senses these movements only through the faintest changes in gas exchange. A breeze lowers oxygen exchange further. A storm lifts it briefly. The sum over years remains nearly the same. The scarcity of oxygen changes what life can do. Cells that rely on oxygen for high energy yield remain confined to the thinnest shells of water and sediment. Metabolisms that tolerate sulfide or use metals as electron acceptors gain space and time to diversify. Enzymes that need trace metals struggle when those metals precipitate in sulfidic depths, and so communities adjust their ratios of nitrogen fixation, carbon fixation, and sulfur cycling to match local supplies. The atmosphere, though thin in oxygen, still mediates these choices by setting the ceiling for how much oxidizing power can enter from above. When winds strengthen surface, oxygen rises slightly, and the photic zone deepens by a small margin. When calm returns, the boundary climbs upward again, squeezing oxygenic life against the lighted surface. Over wider scales, the air's composition guides climate. With oxygen low and carbon dioxide moderate, the greenhouse effect holds temperatures in a temperate band. Without forests or soils rich in organic cover, seasonal swings remain muted along the coasts and broader on the inland plains. The pale sky scatters light differently, giving midday an even illumination that remains visible in the way shadows soften on eroded hills. Clouds tend to be layered and thin. Convective towers are rarer without abundant surface heating, and forests that pump moisture upward. The hydrologic cycle works, but without drama, long dry spells braided with gentle rains that carry dissolved ions and fine clays toward the sea. On these climates, the air writes a stable script that repeats across hundreds of thousands of years. Geologically, the record of faint air hides in proxies that capture the boundary between oxidation and reduction. In red beds that fade upward into grey shales, in iron formations that reappear in thin lenses, in sulphur-rich black shales that lack signs of widespread oxygen, the crust retains a layered memory. Carbonate rocks carry the isotopic imprint of organic burial versus oxidation. When burial temporarily increases, the atmosphere gains a little oxygen, and the ocean surface responds with clearer water. When weathering or remineralization pushes oxidation of old organic matter, the atmosphere loses oxygen, and the sea darkens. The air above records both trends not in color or wind, but in the accumulation of gases that are difficult to measure, except by the minerals they leave behind. The faintness of the atmosphere also shapes the energy of storms and the frequency of lightning. With fewer oxidants and different aerosol loads, cloud microphysics prefers broad sheets to towering cells. Thunderheads still rise where warm seas meet warm coasts, but they are rarer. Each strike of lightning has less chance to make flame in a world where oxygen cannot feed combustion. In the absence of fire, soils remain largely undisturbed by heat, and charcoal does not accumulate in sediments. This absence will one day serve as a quiet marker for the geologic interval, a negative sign as telling as any deposit. At sea, the meeting place of air and water sets the tone for the world beneath. Waves break and pull the atmosphere into spirals that carry oxygen a short distance downward. Bubbles rise and burst, returning a mix of gases to the wind. The exchange is small in content but large in consequence, because it defines the thickness of the habitable skin. In upwelling zones, the faint air meets reduced water from the interior, and an instant of chemistry follows iron, oxidizes, sulfide converts to sulfate, and oxygen disappears. The plume that results falls slowly raining particles that fuel life in deeper sediments. The air overhead remains essentially unchanged, its oxygen soon replaced by daylight production elsewhere along the coast. The scale of the biosphere has learned to match the scale of the atmosphere that feeds it. All of these patterns, thin ozone, low oxygen, soft clouds, dim seas, hold steady across long stretches of time. The planet wears a quiet face. The continents do not green. The oceans do not blaze with oxygen-rich colour. Instead, the world inhabits an intermediate state where surface processes keep order, and deeper processes reset the chemical storehouses that control redox. The faint air is not an accident, but the natural outcome of fluxes that meet and cancel. Daylight builds a shallow stock of oxygen, darkness spends it, and morning begins again with the same small margin. Above the dark seas, the atmosphere drifts light, and nearly constant setting limits that life respects and works within, and writing into stone the record of a planet content for now with a lesser breath. The deep sea changes character, once again sliding from shadowed to fully anoxic. The slow retreat of oxygen through the mid-Proterozoic leaves behind a planet ruled by sulfur. Hydrogen sulfide begins to occupy waters that once merely lacked oxygen, forming broad layers of chemical darkness beneath thin livable skins. In these basins, a new kind of equilibrium takes hold, one defined not by oxygen diffusion from above, but by the steady production of sulfide from below. Microbial life carries the responsibility for both. On the sea floor, dense communities of bacteria reduce sulfate from seawater into hydrogen sulfide, feeding on buried organic matter. The gas diffuses upward, meeting the oxygen that trickles down from surface waters. At the point where the two worlds meet, their reactions form ribbons of minerals, iron sulfides, elemental sulfur, trace oxides, marking a boundary between life's rival chemistries. Above it, green waters shimmer with oxygenic photosynthesis. Below, black and purple layers of sulfur bacteria drift through chemical haze. The Canfield Ocean, named for its modern discoverer, has spread across the world's Middle Ages of oxygen. This is not a sudden change, but a long expansion. Each century adds another metre of depth to the sulfidic zone, each million years another shelf or basin. At first, it affects restricted seas where circulation is poor and organic matter rich. Then it reaches continental margins drawn outward by weak overturning currents that fail to refresh the deep ocean with oxygen. The abyss becomes nearly uniform in its anoxia. Vast tracts of deep water turn corrosive to metals dissolving iron and manganese that once precipitated. When upwelling stirs these waters toward the surface, they carry both nutrients and poisons. In some coastal regions, this infusion sparks brief blooms of photosynthetic life. In others, it suffocates what little oxygen remains. The feedback is relentless. More productivity means more organic matter sinking and decomposing, which in turn fuels more sulfide production. Over time, the seas stabilize in darkness and chemistry, rather than light and air. The structure of this new ocean dictates the structure of its life. Oxygenic photosynthesizers retreat to shallows and illuminated shelves where wave action maintains contact with the air. Beneath them, layered microbial populations form like inverted rainbows. Green sulfur bacteria thriving on dim light draw energy from hydrogen sulfide instead of water. Below them, purple sulfur bacteria harvest different wavelengths, creating distinct pigment bands that color the water column. Beneath these chemoautotrophs build their energy not from sunlight but from redox gradients alone. The result is a vertical ecosystem, each layer feeding on the chemistry of the one above and supporting the one below. This arrangement endures for hundreds of millions of years, shaping the ocean's appearance and the rock record alike. Sediments beneath these waters tell of a world comfortable with stasis. Fine laminations accumulate undisturbed by burrowing animals, for none yet exist to churn the mud. Each thin layer captures a day a season, or a few years of slow settling. Organic matter remains well preserved because oxygen cannot reach it. Pyrite nodules form where iron meets sulfide marking zones of reaction that once shimmered invisibly through the water. Over time, entire continental margins become archives of sulfur cycling. When these sediments are uplifted, they reveal to later ages that the Earth once lingered under a regime of low oxygen and high stability, a chemistry frozen in balance. At the planetary scale, the dominance of sulfidic water alters more than biology. Trace metals essential for oxygenic photosynthesis, molybdenum, zinc, copper, become trapped in sulfide minerals and settle out of the ocean. Without these elements, enzymes that manage oxygen metabolism falter. Photosynthetic efficiency declines further, tightening the planet's redox vice. The air remains faintly oxidizing, but no longer gains ground. The total oxygen budget stabilizes near a lower threshold, perhaps 1% of modern values. In this equilibrium, even minor disturbances, volcanic eruptions, changes in nutrient runoff, shifts in continental configuration, can tip local environments between oxygenated and euxinic states. The surface world becomes a mosaic of chemical provinces, each one ruled by a different balance of gas and mineral. Weathering on land continues to feed the sea, but now with different consequences. As oxygen reacts with sulfide minerals in the crust, it generates sulfate, which rivers deliver to the ocean. There it becomes the substrate for microbial sulfate reduction, closing the global sulfur cycle. Each atom of oxygen used in weathering ultimately re-emerges as hydrogen sulfide in the deep sea, neutralizing any net gain. Even the air's thin oxidant layer depends on this cycle's incomplete closure. If the loop were perfectly balanced, oxygen would disappear entirely. Instead, it survives at a marginal level enough to maintain the ozone shield and permit daylight productivity along continental shelves. The Canfield Ocean feeds upon that balance, drawing sustenance from the planet's hesitation between oxidation and reduction. In this environment, climate remains moderate, neither frozen nor overheated. Carbon dioxide levels are higher than today, but lower than during the Archean. Greenhouse warming offsets a dimmer sun, while high atmospheric methane is curtailed by residual oxygen. The surface temperature holds within a range that allows liquid water everywhere. Yet the appearance of the world from space is unlike any modern view. The oceans are darker, tinted green-brown by plankton and dissolved metals. Shallow seas near land glow with patches of green and violet where bacterial pigments concentrate. No coral reefs, no kelp forests, no fish disturb the smooth gradients of colour. The continents remain subdued, covered in weathered rock and microbial crusts that darken when wet. It is a quiet planet, chemically alive but biologically simple. In this state, the Earth learns to recycle itself efficiently. Every molecule of organic carbon produced by photosynthesis soon finds its way to bacteria that oxidize it with sulfate rather than oxygen, producing sulfide that feeds yet another loop of reactions. The ocean becomes a machine of chemical repetition, turning energy over without storing much of it as biomass. Evolution slows, constrained by low energy yields and stable conditions. Genetic innovation still occurs, new enzymes, new pathways, but the absence of strong environmental pressure allows most life to persist as variations on ancient forms. The planet's surface seems frozen in time, and yet beneath that stillness feedbacks are aligning for change. As sediments rich in pyrite and organic carbon accumulate, they lock away reduced material that would otherwise consume oxygen. Over millions of years, this burial adds tiny increments to the planet's oxygen reservoir. Meanwhile, tectonic processes slowly reorganize continents, altering currents and nutrient distribution. These long cycles will one day weaken the stability of the Canfield Ocean, but for now it reigns unchallenged. The atmosphere above remains pale, the air quiet, the seas dark. The Earth has entered its long Proterozoic equilibrium, where sulfur rules the depths, oxygen skims the surface, and life waits unaware that its chemistry is slowly writing the conditions for its own renewal. In the dim layers of the Canfield seas, life persists in microscopic kingdoms unseen by any later world. Every grain of sediment, every filament of microbial mat hosts societies of cells adapted to the sharp gradients of light and chemistry. These are the sovereigns of the mid-Proterozoic ocean bacteria and archaea, whose metabolisms shape the planet's cycles of carbon, sulfur, nitrogen, and iron. Their domains are measured not in meters but in microns, yet their reach extends from the deepest mud to the edge of the atmosphere. In this long age of low oxygen, they are the engineers of stability, quietly controlling the flow of elements that maintain Earth's faint equilibrium. The shallows glow faintly green each morning as cyanobacteria awaken to light. In these photic zones, photosynthesis still proceeds, producing oxygen that diffuses outward in tiny pulses. Most of it vanishes before escaping the water, consumed by reactions with sulfide iron or organic matter. Yet this local oxygen sustains entire ecosystems. At the surface, small colonies of microbes that oxidize iron, others that process nitrogen, and layers of phototrophs that shift pigments through the day to capture different wavelengths. They build stromatolites that rise slowly from the seafloor, trapping sediment and recording every tide. The rhythmic alternation of oxygen and sulfide across a single day defines their habitat more precisely than any season or year. Beneath this surface activity lies another kingdom fed not by sunlight but by chemistry. Here, sulfate-reducing bacteria dominate using sulfate from seawater to oxidize organic matter and release hydrogen sulfide. They form dense mats that ripple with gases and minerals, creating subtle textures later preserved as lamination in shale. Nearby methanogens convert carbon dioxide and hydrogen into methane, venting it into the water column, where it is often oxidized before reaching the air. Their interaction with sulfate reducers forms a closed loop that recycles carbon between its oxidized and reduced forms without requiring atmospheric oxygen. The deep sedimentary layers layered with organic matter are home to slow metabolisms that persist for centuries within the same pore spaces. Every molecule of carbon or sulfur here passes through dozens of microbial hands before reaching rest. Between these realms of light and dark, a narrow intermediate zone supports a diversity of metabolic hybrids. Microbes able to switch between oxygenic and anoxygenic photosynthesis flourish when conditions fluctuate. Others use nitrate or ferric iron as oxidants when oxygen disappears. In this middle layer, iron oxidation and reduction occur side by side, producing fine-grained minerals that later harden into bands of jasper and magnetite. The microbes themselves leave little trace beyond these mineral signatures, but their chemical legacy endures across billions of years. The variety of their metabolism suggests an evolutionary creativity driven not by crisis, but by the abundance of gradients. The planet offers countless combinations of redox couples, and life explores them all. These microbial systems do more than survive, they govern the planet's long chemical stillness. By regulating how much carbon and sulfur are buried or released, they control atmospheric composition more precisely than volcanoes or weathering. When organic burial increases, oxygen levels rise slightly. When sulfate reduction outpaces burial, oxygen falls. The feedback loops are slow, but stable, operating over spans that make continents drift like tides. In this self-regulated world, microbes act as both cause and consequence of geochemical balance. Their collective activity ensures that the planet neither collapses into full anoxia nor escapes into rapid oxygenation. It is a planetary metabolism with no central nervous system, only the distributed intelligence of countless cells responding to their surroundings. On the ocean floor, mats of sulfur bacteria and iron oxidizers form living carpets that ripple under gentle currents. Each layer competes for light and electron donors, but together they form a cooperative structure where waste from one serves as food for another. These biofilms stabilize sediments, preventing erosion and promoting the slow accumulation of organic material. When storms pass or tectonic uplift shifts, a basin fragments of these mats are buried intact, sealing organic carbon away for future oxidation. Over time, entire sequences of rock become composed of these microbial relics. They are the fossils of an unseen age, preserving the shape of processes rather than the forms of organisms. The chemical influence of these communities extends even to the open ocean. In waters where oxygen still lingers, nitrifying bacteria oxidize ammonia to nitrate, providing nutrients that cycle upward into the photic zone. In deeper layers, denitrifiers reverse the process, returning nitrogen to the atmosphere as gas. Each molecule of nitrogen thus passes repeatedly through microbial hands, ensuring continuity of the biosphere's essential element. The same balance applies to iron, manganese, and trace metals. Every oxidation state finds its counterpart somewhere in the water column, maintained by the slow, continuous labor of life. Temperature, salinity, and light define the geography of these dominions. Near equatorial shelves, warm stratified water supports thick microbial mats. Nearer the poles, cooler conditions allow more mixing and brief oxygen incursions. Yet no part of the sea is completely free of life. Even the deepest anoxic basins host microbial communities that feed on ancient organic matter, diffusing from sediments. They exist at energy levels barely above maintenance, dividing perhaps once in centuries. Their endurance proves that life can persist under conditions almost indistinguishable from death. On land, the microbial presence is sparser but not absent. Soils are thin, lacking roots. Yet microbial crusts coat damp surfaces and river margins. These films fix nitrogen and carbon, releasing small amounts of oxygen that vanish quickly into the mineral matrix. In arid zones, they form dark pavements that stabilize dust and influence weathering rates. Through rain and runoff, they connect continental chemistry to the sea-linking atmospheric oxygen to the deep cycles of sulfur and carbon. The reach of microbial dominion thus extends from the highest exposed rocks to the deepest basins. Over geological time, these layered ecologies alter the composition of the planet itself. Sulfide minerals accumulate in vast quantities, locking away metals that once circulated freely. Organic-rich sediments thicken, preparing the raw material for future hydrocarbons. Even the isotopic composition of the oceans drifts slowly under the cumulative weight of microbial activity. Sulfur isotopes record the balance between oxidized and reduced reservoirs. Carbon isotopes trace the alternation of burial and oxidation. In these signatures lies the chemical autobiography of life's dominion, written in ratios and minerals rather than words. For hundreds of millions of years this regime persists. The world outside changes only slowly. Continents wander. Volcanoes exhale, mountains erode. But within the microbial sphere, countless interactions continue unbroken. The oceans remain layered, the air faint and the planet stable. Energy flows through cells, through sediments, and back to the atmosphere with almost perfect efficiency. The surface of the Earth has become a closed system sustained by the invisible labour of microbes. Their presence ensures that oxygen never vanishes completely, yet never accumulates enough to change the rules of existence. In the dim glow of the can-filled world, they reign without challenge, the quiet architects of a biosphere that neither evolves rapidly nor collapses. Theirs is an empire without movement, without monument, but vast beyond imagination. On the continents, the same sun that powers microbial life at sea also drives the slow disassembly of rock. Rainwater, thinly acidic from carbon dioxide dissolved in the air, seeps into mineral grains and begins reactions that release ions into solution. Over eons, rivers gather these products, calcium, magnesium, silica, phosphorus, and trace metals and carry them across floodplains toward the ocean. The process is relentless but quiet, a planetary pulse that converts solid crust into sediment and nutrients. Each droplet that falls on bare stone participates in a cycle that ties the fate of the continents to the chemistry of the seas. In this mid-Proterozoic world where oxygen remains faint and biological demand, low weathering acts as the main mediator between land and ocean. The balance of these fluxes decides whether the planet's oxygen will persist or vanish entirely. The absence of vegetation means there are no roots to accelerate erosion or stabilize soil. Instead, chemical weathering depends on the interplay of temperature, rainfall, and the reactive surface area of rock. In equatorial zones where air is warm and humid, minerals dissolve, readily producing clays and releasing elements such as phosphorus that are essential for photosynthesis. In cooler regions nearer the poles, the process slows, preserving crustal stability for millions of years. The overall rate of nutrient delivery to the ocean is low by modern standards, but steady enough to sustain microbial productivity in shallow waters. Phosphorus becomes the limiting reagent of life's chemistry. When weathering intensifies, Oxygen production rises modestly, and when continents dry or rivers shrink, the biosphere contracts. The link between erosion and atmospheric composition tightens with every passing age. In the rivers themselves, chemistry changes along the flow. Near their sources, waters run clear and undersaturated, leaching ions from fresh rock. Downstream they turn turbid and enriched, bearing iron, sulfate and carbonate that testify to the redox state of the crust. Some of these ions will feed the open ocean, others will precipitate in estuaries where tides mix salt and fresh water. Here, thin mats of microbial life form on mudflats, processing the chemical cargo before it reaches the sea. They oxidize iron where oxygen exists, reduce sulfate where it does not, and trap sediment beneath organic films that dry and crack with the tide. Each film represents a small transaction between continents and ocean, a negotiation of elements that decides how much oxygen the planet retains. Once in the marine realm, these continental nutrients alter the chemistry of life's foundation. Phosphorus and nitrogen drive productivity, while trace metals like molybdenum and copper determine the efficiency of enzymes that manage oxygen reactions. The scarcity of these metals under sulfidic conditions limits how far photosynthesis can expand. Yet every influx of fresh material from land temporarily recharges the system, promoting localized blooms. When productivity surges, more organic carbon sinks to the seafloor, increasing the potential for oxygen accumulation. But when the buried carbon later oxidizes or dissolves, the gain evaporates. The Earth's atmosphere breathes through this geochemical lung, inhaling oxygen during phases of strong weathering, and exhaling it when sedimentary recycling dominates. The continents themselves shape this rhythm through their arrangement. In this age, land masses cluster into large assemblages that break and reform over time supercontinents such as Nuna and later Rodinia. Their positions determine rainfall patterns and river discharge. When continents cluster near the equator, humid climates enhance chemical weathering, enriching the seas with nutrients and stimulating oxygen production. When they drift poleward or assemble into dry interiors, aridity suppresses the flux, leading to reduced productivity and an expanding anoxic ocean. Tectonic motion thus governs the planet's redox balance through the slow choreography of continents and seas. The atmosphere responds on timescales so long that each shift appears as a minor variation within a greater stillness. Volcanoes continue to play their part in this cycle, releasing carbon dioxide that replenishes the weathering agents. Their eruptions also emit sulfur gases that convert to sulfate aerosols, influencing climate and ocean acidity. When volcanic activity increases, temperatures rise slightly, accelerating weathering. When it wanes, the planet cools, slowing the same reactions. Over millions of years, this negative feedback stabilizes climate, but does not eliminate its gentle oscillations. The interplay of weathering, volcanism, and biological productivity creates a loop that holds the planet in temperate equilibrium, despite the dimmer sun. Beneath the seas, the input of continental material transforms the sedimentary environment. Fine clays and dissolved ions delivered by rivers settle onto the continental shelves, mixing with organic matter from microbial mats. In these layers, phosphorus can become trapped within minerals or released again during early diagenesis. The balance between these two outcomes decides how long the nutrient remains available. If burial dominates, productivity declines. If regeneration prevails, it continues. Over time, the gradual thickening of sediment acts as both archive and engine of planetary metabolism. Each new stratum records the interplay of oxygen, carbon, and sulfur, while continuing to influence them through slow chemical reactions. Even as weathering feeds the deep, it also draws down atmospheric carbon dioxide. The formation of carbonates removes carbon from the air and locks it into rock, helping regulate temperature. This removal would cool the planet were it not for counteracting volcanic outgassing. The steady pace of both processes defines the moderate climate of the Proterozoic. The absence of large ice sheets and the rarity of glacial deposits indicate a world kept just warm enough for liquid water. Yet the equilibrium is fragile. A small change in continental area or mountain height could alter the balance between greenhouse retention and carbon drawdown, tipping climate toward cold or warmth. The interaction between land and sea extends beyond chemistry to physics. Sediment carried by rivers changes the shape of continental shelves, influencing ocean circulation. Fine grains form barriers and deltas that redirect currents, affecting where upwelling brings nutrients to the surface. These changes in turn modify biological productivity and oxygen exchange. Through such feedbacks, the quiet erosion of rock participates in shaping planetary respiration. The continents, though barren of vegetation, act as lungs for the world, exhaling minerals that sustain the ocean and indirectly the atmosphere. In some coastal zones where fresh and saline waters meet, striking colour gradients reveal the ongoing chemistry. Pale green where oxygen persists, yellow where iron oxidizes violet, where sulfur bacteria gather black where anoxia dominates. The pattern shifts with tide, storms and seasons. Each hue marks a fleeting boundary between processes that define Earth's redox balance. Over centuries, these zones migrate with changing sea level, leaving layered sediments of alternating composition. In cross-section, they appear as rhythmic bands, each a moment of negotiation between oxygen and its absence. The cumulative effect of continental weathering across millions of years is subtle but decisive. Without it, the ocean would lose nutrients and the biosphere would fade. With too much oxygen would rise rapidly and destabilize the chemical feedbacks that keep the atmosphere thin. The mid-Proterozoic finds its stability in moderation. The continents erode at rates that maintain the faint glow of life without igniting new evolutionary fires. From space, the Earth of this era would appear as a tranquil sphere, low clouds, soft oceans and wide expanses of rust-coloured land. Beneath that, calm rivers carry the memory of mountains to the sea, and through their endless transport of dissolved minerals, they sustain the chemical breath of a planet that endures by wearing itself away. The long equilibrium of low oxygen is not perfectly steady. Across millions of years, faint and temporary recoveries interrupt the calm, leaving chemical signatures in the rocks that later ages will recognize as positive carbon isotope excursions. These are the transient blue moments of the Proterozoic world intervals, when the planet seems to inhale a little deeper, when the atmosphere brightens, and the ocean surface turns slightly clearer before subsiding again. The causes are varied and often overlapping: subtle increases in nutrient supply, rearrangements of continents, shifts in volcanic degassing, or changes in microbial evolution that alter how carbon and sulfur move through the environment. Each episode of recovery begins quietly, spreads unevenly, and fades back into the slow breath of the planet. The air never reaches more than a few % of modern oxygen levels, but for a time it becomes strong enough to alter the colour of light and the chemistry of the sea. In one of these intervals, perhaps following a period of intensified weathering or tectonic uplift, phosphorus delivery to the ocean increases. Photosynthetic microbes respond quickly, blooming across continental shelves and shallow lagoons. With higher productivity comes greater burial of organic matter, removing reduced carbon from the system and allowing oxygen to accumulate. The thin atmospheric reservoir swells slightly. The change is imperceptible on human scales, but evident over millions of years as a global signal. Iron formations become less common, replaced by carbonates that form in clearer, more oxygenated waters. Sulfur isotopes shift toward values indicating stronger sulfate oxidation. The world glows faintly brighter under a sky that carries more ozone and scatters light in deeper shades of blue. In these intervals, the ocean stratification relaxes a little. Where previously the chemocline, a boundary separating oxygenated and anoxic layers, had lain close to the surface, it now sinks deeper. Mixing increases, bringing trace metals from below to feed photosynthesis above. Shallow waters become less hostile to aerobic life, and microbial mats extend farther offshore. New lineages of bacteria that tolerate higher oxygen levels proliferate, adjusting enzyme systems that use copper or molybdenum elements, scarce during euxinic times, but newly accessible under partial reoxidation. The interplay between nutrient availability and metal chemistry becomes the unseen engine of these recoveries. Yet each improvement in oxygenation sows the seed of its own decline. As oxygen rises, it promotes weathering on land that draws down carbon dioxide, cooling the climate and reducing the rate of chemical erosion. With less nutrient input, productivity wanes and oxygen falls again. The cycle closes quietly, leaving behind mineral and isotopic markers of its passage. The transient nature of these blue moments ensures that life remains limited to microbial forms. Higher oxygen could in principle support more energetic metabolisms, but the environment never stays favourable for long. Each pulse of oxidation strips the ocean of easily available nutrients, or triggers the precipitation of essential trace metals, reimposing the chemical constraints of the Canfield world. The result is a biosphere that oscillates between slightly improved and deeply reduced conditions, a planet whose metabolism stutters but does not evolve. In the sediments, these fluctuations appear as alternating bands of black and grey shale, each representing a swing in redox state. Positive carbon isotope anomalies mark the peaks of oxygenation, while return to baseline or negative values signal renewed reduction. The pattern repeats across tens of millions of years, forming a geochemical rhythm that mirrors the breathing of the planet itself. Climate too may respond to these shifts. As oxygen rises and organic burial increases, carbon dioxide levels decline, allowing global temperatures to drop. Some of the Proterozoic's mild glaciations may have coincided with such intervals. Yet these ice events remain limited, constrained to high latitudes and short durations. The feedbacks between weathering, carbon burial and volcanism prevent runaway freezing. When volcanic outgassing replenishes carbon dioxide, warming resumes, and the system resets. Through it all, oxygen levels follow the same oscillation, rising slightly in the cool phases, falling as warmth returns. The planet maintains its middle course, rarely veering far from equilibrium. In the air, the differences would be subtle but noticeable to an observer. During oxygen-rich intervals, haze diminishes and sunlight sharpens. The sky appears more vividly blue at midday, and the ultraviolet radiation reaching the surface weakens as ozone thickens. At night, atmospheric glow increases faintly, a result of higher oxygen recombination in the upper layers. During declines, the haze returns muting colour and restoring the soft, diffuse light characteristic of the mid-Proterozoic. These optical changes, minor by modern standards, mark the living pulse of the planet's redox cycle. In the ocean, the transitions shape entire ecosystems. As oxygen expands downward, sulfur bacteria retreat their pigment-rich mats, replaced by communities that rely on iron or nitrate as electron acceptors. When oxygen recedes, the sequence reverses. In some basins, these layers migrate vertically by hundreds of meters over geological time, creating alternations in mineralogy and color that will later guide geologists to reconstruct the pattern of Proterozoic breathing. Iron oxides give way to pyrite, then return again. Carbonate platforms shift between dull grey and pale orange as redox boundaries rise and fall. Each transformation leaves a whisper of oxygen's brief dominion before chemistry reclaims the depths. The microbial response to these episodes illustrates the resilience of life. Populations expand when conditions favour oxygen and contract when they do not, but the core diversity of metabolisms remains intact. New genetic variants evolve to exploit the intermittent presence of oxygen enzymes that manage reactive oxygen species membranes, that tolerate oxidative stress pathways that use oxygen in trace amounts without dependence on it. These innovations, developed in the quiet repetitions of the Proterozoic, will one day form the biochemical foundation for more complex organisms, yet at this time their function is merely survival in a fluctuating world. Geochemical data suggest that each of these transient oxygenations may have lasted several tens of millions of years before fading. In the rock record, they appear as sustained positive carbon isotope excursions, often followed by compensating negative swings as the system returns to baseline. The Lomagundi-Getuli event early in the Eon remains the largest of these, but smaller echoes persist through the middle Proterozoic marking moments when the Earth nearly recovered its lost breath. The persistence of such cycles indicates that the planet's interior and surface processes remained delicately coupled volcanic gases, providing reduced material weathering and burial supplying oxidation with life mediating between them. The balance is precise enough that neither side ever wins for long. Over the long term, these fluctuations contribute to gradual change. Each pulse of oxygenation leaves behind oxidized sediments, sulfates, and weathered crust that alter the starting conditions for the next cycle. The cumulative effect is a slow enrichment of the surface in oxidized minerals and an incremental rise in baseline oxygen. The world does not leap toward modern conditions, but inches forward through repetition. The transient blue moments are not failures of stability, but steps in the long path toward higher oxidation. Still within the scale of the mid-Proterozoic, they remain temporary reliefs, clearings in an otherwise dim atmosphere. Seen from orbit during such a phase, Earth might appear subtly different. Oceans would look less brown-green, reflecting more light from their shallower oxygenated layers. The continents still barren would display brighter tones where iron oxides renewed their colour. The air would show a faint deeper blue along the limb, an indicator of thicker ozone, but to the microbial life inhabiting its waters the world would feel unchanged, a repeating cycle of light and shadow oxygen and sulfide life and chemical rest. When the oxygen finally declines once more, the sea darkens, the haze returns, and the planet settles back into its long, quiet breath, carrying forward the memory of its brief brightness. The reprieve of blue light fades as the oceans retreat once more into darkness. The boundary between oxygen and anoxia rises toward the surface, and the chemical front that once lay deep beneath the waves creeps upward, staining the shallow seas with the mark of sulfur. Hydrogen sulfide, the product of sulfate reduction in buried sediments, begins to accumulate again in mid-depth waters. In the still basins of the mid-Proterozoic, weak circulation prevents oxygen from replacing what is lost. Each pulse of decomposition draws more sulfate from the overlying water, fueling the microbes that thrive on its reduction. Within these slow exchanges, the sulfur veil returns, spreading across continental margins and deep shelves like an invisible tide. The world darkens chemically, though its climate and geography remain unchanged. This is not a catastrophe, but a reversion, an ocean resettling into the equilibrium that has defined most of its history. In these waters, the concentration of hydrogen sulfide rises until it saturates entire basins. The gas reacts with dissolved iron to form pyrite-turning sediments beneath into dark, fine-grained layers that trap the record of an anoxic world. The transformation is silent but profound. With oxygen largely absent elements essential for higher energy life such as molybdenum and copper precipitate into insoluble sulfides and sink. The enzymes that depend on them become scarce, and photosynthetic oxygen production falters. Sulfide itself is toxic to many microbial groups that once occupied the boundary zone, forcing communities to contract toward the surface. Only a narrow stratum of light and oxygen remains habitable. Below it, metabolism belongs to organisms that draw energy from sulfur compounds directly. The water turns greenish-black where sunlight penetrates only a few meters before scattering through bacterial pigments. Hydrogen sulfide also leaks into the atmosphere above stagnant regions, where it meets oxygen and forms a faint haze of sulfur aerosols. These particles reflect sunlight and alter the radiative balance, dimming the surface by a small degree. The effect is not global cooling, but a gentle shading, another layer of restraint added to the planet's slow metabolism. Each molecule of sulfide that rises from the sea consumes oxygen in the air, tying the fate of the atmosphere to the chemistry of the depths. The Earth becomes a connected circuit of oxidation and reduction that operates not through violence, but through endless repetition. In shallow lagoons where currents still bring intermittent oxygen, the contrast between life and death sharpens. Mats of cyanobacteria flourish during mixing events when wind stirs air into the water, only to collapse when the calm returns and sulfide builds up again. Layers of dead cells settle and feed sulfate-reducing bacteria below, completing a short but efficient cycle of organic matter. Each generation builds the foundation for the next, without leaving much oxygen behind. Stromatolites continue to grow, but at slower rates, their laminae tighter and darker, recording seasonal shifts in chemistry rather than growth. These structures will later reveal to scientists the fluctuating nature of the mid-Proterozoic seas, with alternations between oxygenic and sulfidic phases pressed into stone. The sulfur veil changes not only the oceans, but also the pathways of global nutrient exchange. With oxygen scarce, nitrogen-fixing bacteria lose many of the metals required for their enzymes, making nitrogen a limiting nutrient. As a result, productivity declines further, deepening the redox divide. The planet now runs on minimal fluxes of energy and matter, each cycle stretched to its limit by scarcity. In such an environment, stability is preserved through exhaustion. The system cannot collapse because it already operates near zero growth. Every feedback balances another, every reaction meets its counter-reaction. The Earth drifts through time with a steady, almost imperceptible rhythm. Even as sulfide dominates the sea, there remain refugees of oxygen. Coastal upwelling zones and certain semi-enclosed shelves continue to host photosynthetic life that produces local oxygen surpluses. These patches act as lungs for the planet, small but persistent. Over time, their sediments capture more organic matter than surrounding regions, subtly increasing oxygen release to the air. Yet each attempt at recovery is checked by the spreading of sulfidic water from adjacent basins. The system behaves like a slow pendulum, oscillating around a stable mean without crossing into new territory. The Earth's redox state remains poised between stagnation and renewal, its progress limited by the very feedbacks that keep it stable. The chemistry of the air reflects this new balance. Oxygen remains at perhaps 1% of modern concentration, enough to sustain a thin ozone layer but not enough to support combustion or complex life. Carbon dioxide stays moderate, balanced by weathering and volcanism. Trace gases like methane and nitrous oxide rise slightly as anaerobic metabolisms expand. The atmosphere is clear yet subdued, its composition stable enough to resist major climate swings. Clouds form from aerosols seeded by sulfur compounds, their diffuse cover softening sunlight into a constant pale tone. From orbit, the planet glows with muted color, its oceans darker than before, its continents faintly red. Within the deep sediments, microbes continue to shape minerals from the byproducts of their respiration. Iron sulfides accumulate as nodules and bands, preserving the memory of each rise and fall in sulfide concentration. Over time, the accumulation of these minerals locks away large quantities of reduced sulfur, creating a geological sink that balances the global budget. Every atom of sulfur buried as pyrite frees an equivalent of oxygen to the atmosphere, but the process is so slow that it never overtakes the ongoing consumption at the surface. The Earth maintains its equilibrium through a series of balances so finely tuned that they appear intentional, though they are merely the sum of physical and biological persistence. Life within the sulfur veil remains abundant though small. Filamentous sulfur bacteria form visible mats on the seafloor, their twisted chains waving gently in currents. Some store nitrate or elemental sulfur within their cells, allowing them to switch metabolisms when conditions change. Others form symbiotic associations, passing electrons from one population to another through microscopic structures. These networks constitute the planet's most efficient ecosystems, recycling energy through closed loops that produce little waste. The slow pace of evolution here does not signal stagnation, but adaptation to permanence. In the steady world of the Proterozoic, constancy itself becomes the ultimate success. On land, the effects of the sulfur cycle are indirect but pervasive. Weathering of exposed sulfide minerals on the continents releases sulfate, which feeds the same bacterial reduction in the ocean. This connection forms a planetary loop linking atmosphere, land, and sea. Each rainstorm that oxidizes pyrite in mountain rocks contributes to the growth of sulfide layers in marine sediments thousands of kilometers away. Over millions of years, this transfer leaves behind extensive deposits of sulfur-bearing rock that will mark the eon's chemistry for the rest of Earth's history. By the close of this interval, the sulfur veil has stabilized. The oceans remain largely euxinic, yet the atmosphere persists, never collapsing into total anoxia. The balance between burial and release, between oxidation on land and reduction in the sea, continues to hold. The world is neither improving nor decaying. It is simply existing within parameters that have become self-enforcing. To an observer, time would seem to slow the color palette of the planet, reduced to muted greens, browns, and greys. Beneath that quiet surface, chemistry continues its ceaseless work, writing invisible equations that keep the faint breath of oxygen alive above a sea of sulfur. The silence of the mid-Proterozoic world hides a continuous conversation between atoms. In the absence of complex life, the planet speaks through isotopes, subtle variations in the weights of its elements that record each reaction, each brief rise or fall of oxygen. These signatures, locked within carbonates, shales, and sulfides, form the most faithful memory of an age otherwise devoid of fossils. Carbon isotopes trace the difference between organic matter buried and oxidized. Sulfur isotopes carry the imprint of bacterial reduction in anoxic seas. Iron isotopes mark the shifting boundaries between oxidation and reduction in water columns and sediments. Together they capture the planet's pulse, revealing that the apparent stillness of this long epoch conceals countless oscillations of chemistry. The rocks remember what the air and ocean forget, writing in atomic ratios the story of how oxygen almost vanished but never did. Every molecule of carbon dioxide that enters the ocean faces a choice to be fixed into organic matter by photosynthesis, or to remain dissolved and eventually return to the air. The fraction of carbon that becomes buried controls the isotopic balance between heavy and light carbon. When burial rates are high, the ocean and atmosphere grow enriched in heavy carbon, producing positive isotope values. When oxidation dominates, light carbon returns, driving the signal downward. Through this proxy, the Earth's deep time carbon cycle reveals the faint rhythm of life and its coupling to oxygen. Each pulse of positive carbon isotopes marks a time when oxygen briefly rose, and each decline signals its loss. The pattern repeats endlessly through the mid-Proterozoic, the rock record serving as a diary of the planet's shallow breathing. Sulfur isotopes add another dimension to this memory. In the sulfidic seas of the Canfield world, sulfate-reducing bacteria prefer lighter sulfur, leaving the heavier isotope behind in seawater. When sulfide minerals form and settle, they remove light sulfur from the system, enriching the remaining sulfate in heavy isotopes. Over time, these processes inscribe alternating layers of isotopic enrichment and depletion, each representing a fluctuation in microbial activity and ocean redox. Where isotopic separation is large, it indicates abundant sulfate and active biological cycling. Where it narrows, sulfate scarcity or widespread euxemia restricts fractionation. The variations are small, measured in parts per thousand, yet they reveal shifts of planetary scale. The sulfur isotopic archive confirms what the carbon record suggests, that the Proterozoic was not static, but dynamic in slow motion. Iron too participates in this isotopic conversation. Dissolved ferrous iron, rising from anoxic depths, oxidizes to ferric iron when it encounters oxygen, and in doing so it fractionates isotopes. The resulting minerals carry subtle fingerprints of their formation environments. Layers of alternating iron isotopic composition in sedimentary rocks indicate repeated incursions of oxygenated water into otherwise anoxic basins. The persistence of these variations shows that oxygen never fully retreated from the surface. It hovered as a faint presence, touching the upper ocean from time to time before withdrawing again. Each repetition of this cycle left traces so delicate that only later science could decode them, yet they represent the heartbeat of an entire world. In the absence of plants or animals, these isotopic fluctuations are the only witnesses to the slow dialogue between the biosphere and geosphere. They tell of the interactions among volcanic outgassing, continental weathering, and microbial metabolism. When volcanoes erupt, they inject reduced gases like hydrogen and sulfur dioxide into the air, consuming oxygen. When weathering on land intensifies, it supplies nutrients that promote photosynthesis and burial, generating oxygen. The balance between these forces appears in the isotope record as alternating intervals of enrichment and depletion. Over hundreds of millions of years, the overall trend remains neutral, confirming that the planet's chemistry is locked within a self-stabilizing feedback system. To the naked eye, this interplay is invisible. The continents remain bare, their colors muted by oxidation and dust. The oceans continue to shift between shades of green, brown, and black depending on local redox conditions. Yet beneath these visual constants lies an atomic world in flux. Each rainstorm, each volcanic plume, each microbial bloom sets in motion isotopic exchanges that ripple through the ocean-atmosphere system. The rates are slow, but the sums are immense, and over geological time they shape the composition of entire reservoirs. The air's slight oxygen content, the sea's sulfate concentration, the ratios of carbon dioxide to methane, all emerge from the arithmetic of these countless small transactions. Rocks laid down in this era act as repositories of those transactions. In carbonate platforms that fringe the continents, thick sequences accumulate under stable conditions. Their isotopic uniformity across great distances testifies to the broad mixing of the ocean surface, while minor excursions record local perturbations. In deeper settings, organic-rich shales preserve stronger signals, capturing the contrast between oxygenated shallows and anoxic depths. The consistency of these patterns around the world suggests that the mid-Proterozoic ocean was globally connected, a single, slowly circulating system, governed by similar constraints everywhere. Even when isolated basins became euxinic, the broader ocean maintained the same redox architecture. This global coherence allowed the isotopic memory to synchronize across continents, providing a unified chronicle of planetary balance. Occasionally, extraordinary events disturbed this equilibrium. A burst of volcanic activity or a shift in supercontinent configuration introduces new isotopic signals that stand out against the background calm. These anomalies often correspond to transient oxygenations or declines, revealing how tightly linked tectonics and atmosphere remain. When continents collide and mountains rise, weathering accelerates, drawing down carbon dioxide and enhancing nutrient flux. When they rift apart, increased volcanism restores carbon dioxide and delivers reduced gases that consume oxygen. The isotopic record captures these long negotiations between Earth's surface and its interior. The precision of this natural archive will one day allow scientists to reconstruct the story of oxygen's near disappearance. But within the Proterozoic itself, the processes unfold without awareness. The world simply cycles, each molecule reacting according to chemistry, each isotope moving along pathways defined by temperature, pressure, and energy. The sum of all these motions forms a steady-state world in which nothing changes quickly, yet nothing stays perfectly fixed. Over hundreds of millions of years, the isotopic patterns drift toward values slightly more oxidized, suggesting that slow burial of reduced material is incrementally shifting the balance. The change is so gradual that it escapes notice even in geological time, but it marks the first stirrings of the planet's eventual reoxygenation. From the perspective of the atmosphere, these atomic exchanges are imperceptible. The sky remains pale, the air thin, and ozone continues to filter sunlight enough to preserve surface stability. From space, Earth appears almost timeless, but the rocks forming under its calm exterior are busy storing information that will outlast the age itself. They are silent observers, each crystal lattice encoding the ratio of isotopes that reveal the interplay of life and environment. Through them, the Proterozoic leaves its testimony that the planet did not sleep through its middle years, but instead maintained a slow, thoughtful balance between breath and silence. The isotopic memory endures long after every cell that created it decays. It is a language of fractions and gradients, the mathematics of planetary respiration. In this quiet age when life is microscopic and time stretches beyond imagination, isotopes become the planet's diary, one written not for readers, but for persistence. Each number, each ratio, each atom's slight difference from its neighbour ensures that the story of oxygen's near loss and its patient return will never be forgotten by the Earth itself. The slow oscillations recorded by isotopes fade into a deeper calm. The world enters an interval so prolonged and uneventful that later scientists will call it the boring billion. Yet the label misleads, for beneath the calm surface the planet continues its intricate chemical breathing. Oceans remain stratified, skies remain pale, and continents drift with patient indifference. Volcanic arcs rise and erode, supercontinents merge and separate, yet none of these rearrangements disrupt the quiet equilibrium. It is a world of persistence, of systems balanced so finely that no single process overwhelms another. In this long stillness, oxygen stays near its minimal threshold, enough to sustain the ozone layer, but insufficient to transform life or landscape. The planet appears at peace, but the piece is that of a mechanism running flawlessly, every feedback locked in step. The continents of this era, Nuna, later Columbia, then Rodinia, stretch across the equator low and broad, surrounded by shallow seas that lap at stable margins. The absence of complex vegetation keeps erosion slow, while weathering maintains a steady trickle of nutrients to the ocean. The atmosphere carries little dust, the hydrologic cycle, modest the climate uniform across latitudes. Temperatures remain mild for hundreds of millions of years, with no large-scale glaciations and no catastrophic warming. The sun's output is weaker than today, but greenhouse gases balance the deficit. Each process buffers the next. When weathering removes carbon dioxide, volcanism replenishes it. When organic burial raises oxygen, slightly oxidative, weathering pulls it back down. The Earth behaves like a self-correcting organism, its chemistry tuned to endurance. The oceans mirror this stability. Surface waters continue to host cyanobacteria and green algae, slowly diversifying but remaining microscopic. Below them, anoxic and sulfidic layers persist their boundaries, moving only in rhythm with tectonic and climatic cycles. The chemistry of these layers defines the ecology of the entire biosphere. Sulfate-reducing bacteria dominate the dark depths, producing hydrogen sulfide that diffuses upward until it meets the thin film of oxygen near the surface. Here, photosynthetic life persists in narrow zones where conditions overlap, where light still reaches and toxins have yet to intrude. The spatial compression of habitability ensures that productivity remains low yet steady. The biosphere of this era, though limited in energy, is vast in extent and longevity. Sediments accumulating on continental shelves reflect this uniformity. Laminated shales, black with organic carbon, alternate with carbonates formed in oxygenated shallows. The repetition is near perfect layer upon layer without major interruption. Stromatolites continue to grow in coastal settings, their domes and columns rising through sediment as tidal cycles bury them. Some reach heights of several meters, standing as silent monuments to microbial patience. Their layered structures record years, centuries and millennia of unchanging conditions, each lamina a breath of life and decay in a world untroubled by disruption. These formations dominate the sedimentary record, spreading across ancient shorelines, from one continent to another, the same wherever found. They are the architecture of stability. This equilibrium extends to the deep earth. Tectonic processes slow slightly as the mantle cools, producing fewer volcanic outbursts and smaller arcs of subduction. Continental growth stabilizes and heat flow through the crust declines. With fewer perturbations from below the surface, environment experiences fewer shocks. The magnetic field sustained by convection in the liquid outer core remains strong enough to protect the atmosphere from erosion, ensuring that even the thin oxygen reservoir endures. The interplay between deep and shallow systems functions smoothly, reinforcing the planet's resistance to change. It is as though Earth has settled into a middle-age, mature, self-regulating and calm. Life within this environment adapts to the predictability. Microbial communities diversify not through catastrophe, but through specialization. In the oxygenated shallows, early eukaryotes appear cells with internal membranes and nuclei, though they remain confined to microscopic scales. Their evolution proceeds slowly, driven by minor fluctuations in nutrient availability rather than selective pressure from environmental extremes. Many evolve symbiotic relationships with bacteria exchanging energy and metabolites across invisible boundaries. The lineage of complexity begins here, not in bursts but in long cooperation. Deep in the anoxic zones, archaea and bacteria continue their ancient chemistries, refining pathways for methane production, sulfur reduction, and ion cycling. Evolution operates at low speed, but immense duration, exploring the full range of chemical possibilities within the constraints of limited oxygen. The climate of the long stillness favours persistence. Without plants to draw down carbon dioxide or produce large organic soils, atmospheric carbon levels remain moderate. Clouds spread evenly, reflecting sunlight, but not enough to trigger glaciation. Rainfall patterns follow simple convection belts near the equator, feeding wide rivers that meander across low plains. Storms are mild and no seasonal extremes disturb the steady cycles of erosion and sedimentation. The absence of dramatic events means that geological time blurs. Centuries or millennia differ little from one another. The same microbial mats rise and fall with tides generation after generation, unaware of the scale of their endurance. Though the term boring suggests inaction, the long stillness is a period of deep preparation. Every atom oxidized in these quiet seas, every grain of pyrite buried adds infinitesimally to the oxygen storehouse that will one day transform the world. Each weathering reaction on land, each volcanic emission into air, each sedimentation cycle contributes to the accumulation of oxidized crust and the depletion of reduced gases. Slowly, imperceptibly, the foundations for future oxygenation are being built. The stability that now governs the planet will later serve as the baseline against which upheaval is measured. Without this extended calm, the next transitions could not occur. The isotopic record from this time shows remarkable consistency. Carbon isotope values hover near neutral, indicating balanced carbon burial and oxidation. Sulfur isotopes vary only slightly, reflecting steady sulfate availability and minimal redox fluctuation. These flat lines on future graphs will represent 1 billion years of quiet planetary respiration. Yet even in their monotony, small deviations hint at life's persistence, brief enrichments that suggest localized oxygen oases, tiny downturns that record temporary anoxia. The overall impression remains one of endurance without excitement, the steady hum of a system that has found its long-term rhythm. From space, the earth of the long stillness appears serene. Oceans cover most of the surface darker and more subdued than today, their margins ringed by pale carbonate platforms. Continents are low, their edges fringed by wide continental shelves. The atmosphere is faintly blue cloud decks, thin and even. The visual calm matches the chemical balance below. No ice caps, no desert belts, no sharp seasonal contrasts mark the view. The planet has become a self-sustaining equilibrium machine. Within this stillness, time acquires a different meaning. Processes measured in millions of years replace those measured in centuries. The accumulation of sediment, the drift of continents, the burial of carbon all proceed at rates that seem frozen but never stop. The Earth's deep cycles have settled into resonance, each reinforcing the other's persistence. When viewed across the sweep of the eon, the long stillness is not absence but mastery, the triumph of balance over volatility, of slow chemistry over rapid change. The planet's faint oxygen remains constant, the oceans remain divided, and the biosphere continues its quiet work. The world holds its breath not out of crisis, but because it has no need to exhale. After hundreds of millions of years of stillness, subtle tremors begin to ripple through the steady balance of the Proterozoic Earth. They are not sudden cataclysms, not the kind of eruptions or impacts that mark other ages, but shifts of pattern too slow for any inhabitant to sense. Deep within the mantle, heat continues to accumulate, and the circulation of molten rock beneath the crust strengthens. Old supercontinents begin to rift thin and fracture along ancient weaknesses. As they drift apart, new oceans form and mid-ocean ridges exhale, gases rich in carbon dioxide, sulfur, and reduced compounds. The atmosphere, long held in chemical equilibrium, receives a slow infusion of these volcanic emissions. At first, they vanish into the steady cycles of weathering and photosynthesis, but as continental configurations change, feedbacks begin to wobble. The long stillness, once perfect, now flexes under the weight of its own duration. The supercontinent Rodinia gradually assembles and stabilizes, stretching from pole to pole with vast interior deserts and narrow coastal shelves. Its configuration alters global circulation. Dry interiors accumulate thick deposits of evaporates, while edges experience alternating monsoons and droughts. Rivers that once distributed weathering products evenly across the seas now feed localized basins, creating chemical provinces with distinct salinities and redox states. In some regions, increased runoff enriches the ocean with nutrients, prompting brief bursts of productivity. In others, aridity starves the coastal shallows. The result is patchwork oxygenation, where some seas grow momentarily clearer while others sink deeper into sulfidic darkness. The isotopic signatures of carbon and sulfur begin to waver again, their flat lines bending into gentle oscillations. The Earth's breath, steady for 1 billion years, starts to quicken. In the atmosphere, these changes express themselves through minor fluctuations in oxygen and carbon dioxide. Volcanic activity from new rifts increases the release of reduced gases that consume oxygen, yet simultaneously injects carbon dioxide that warms the climate and enhances weathering. The balance becomes dynamic rather than static. Weathering of Rodinia's highlands accelerates carrying phosphorus into the ocean, which stimulates microbial growth. More photosynthesis means more organic burial, a slight rise in oxygen and an isotopic shift toward heavier carbon. But as burial increases oxygen, fuels more weathering of exposed sulfides on land, creating sulfate that feeds bacterial sulfate reduction in the ocean and generates hydrogen sulfide that counters oxygen once again. The feedback oscillates, never collapsing into extremes but pushing the planet into a pattern of low-amplitude swings. Beneath the surface, circulation patterns in the ocean respond to shifting continents and changing wind systems. New seaways open, and currents begin to flow where none had before. Upwelling intensifies in some regions, bringing nutrient-rich but anoxic water to the surface. These episodes fertilize photosynthesis while also releasing sulfide into the atmosphere, producing localized haze and acid rain that alter continental weathering rates. The global system remains stable in the long view, but on shorter geological timescales, millions rather than hundreds of millions of years, variability grows. Oxygen levels rise and fall, shallow waters fluctuate between clear and turbid, and the colour of the sea alternates subtly between blue-green and brownish-grey. To later observers, these shifts mark the first signs of the Proterozoic's slow awakening. In the shallows, microbial communities adjust to the new rhythm. Some adapt to rising oxygen by developing enzymes to manage reactive oxygen species. Others retreat into deeper sediments where sulfide still dominates. In rare intervals of stronger oxygenation, eukaryotic algae expand, taking advantage of trace metals newly available in less sulfidic waters. Their populations wax and wane with the changing chemistry, leaving faint traces of lipid molecules that will one day be found in rock as biomarkers. These molecules testify that the ocean's surface has become a mosaic of redox states, from nearly modern oxygen levels in one basin to fully anoxic in another. The biosphere begins to divide along chemical lines, each environment selecting its own survivors. The continents still bare of vegetation act as silent participants in this slow transformation. As Rodinia's mountains rise, rainfall increases along coasts, and the erosion of fresh rock releases new nutrients. Glacial deposits begin to appear at higher latitudes, signaling that the climate system is edging toward instability. Short glacial episodes punctuate otherwise warm conditions, perhaps driven by fluctuations in greenhouse gas concentrations tied to the carbon cycle. When glaciers expand, weathering slows and carbon dioxide accumulates. When they retreat, rapid weathering draws it down. Each swing influences oxygen indirectly, adding complexity to what had once been monotone stability. The Earth's climate and redox state are now intertwined more closely than before, their feedback sensitive to geography and time. In the deep ocean, where chemical gradients define the rhythm of life, the new instability manifests as alternating phases of iron and sulfur dominance. When oxygen intrusion strengthens, ferrous iron oxidizes and precipitates, forming thin iron-rich layers. When the intrusion weakens, hydrogen sulfide returns, converting those layers to pyrite. The alternation of these minerals in sediments becomes a precise record of shifting redox fronts. Each band of pyrite or oxide represents thousands of years of subtle environmental motion. The chemical quiet of earlier epochs gives way to layered whispers of change. These gradual perturbations carry no disaster, yet they accumulate momentum. Over tens of millions of years they erode the resilience of the old balance. The planetary oxygen reservoir grows slightly, not by leaps, but through incremental gains each time organic carbon burial outpaces its oxidation. The crust thickens with oxidized minerals, and the ocean's sulfate inventory increases as sulfur cycles expand. These changes are small in each generation, but cumulative in their long-term effect. The system that once held oxygen at a strict minimum begins to loosen. Its controls still function, but their thresholds shift. The Earth's chemical machine is recalibrating itself for a new mode of operation, though it will take many more ages for that transformation to reach completion. The long stillness thus ends not with noise but with complexity. The redox landscape of the planet becomes patchy and variable. The air retains its faint oxygen, but that oxygen now fluctuates across time and space. The ocean alternates between euxenic ferruginous and mildly oxygenated states. Isotopic curves begin to twist, showing richer dynamics. The planet has rediscovered motion within stability, variation within balance. To a distant observer, nothing visible seems to change. The continents remain rust-coloured, the seas dim, the atmosphere pale. Yet in the chemistry of the oceans the pulse quickens. The Earth's metabolic rate after 1 billion years of steady breathing starts to rise. This quiet instability is a prelude rather than a revolution. The system remains far from the oxygen-rich conditions that will one day support complex animals, but the groundwork is being laid. The feedbacks that once held the world in equilibrium now generate oscillations, and those oscillations create opportunities. Microbes that endure alternating redox environments evolve flexible metabolisms. Sediments accumulate alternately oxidized and reduced minerals that will later serve as resources for new chemistry. The world is preparing itself unknowingly for transition. It is as if the long stillness has drawn a deep inhale and now at last begins to exhale. The slow undulations of redox balance grow into wider swings as the Neoproterozoic advances. Subtle isotopic oscillations that once barely disturbed the calm now widen into great arcs across the carbon record. Among them lies the most dramatic of all, the Churyumwinooka event, a prolonged negative carbon isotope excursion that signals a profound oxidation of organic carbon throughout the ocean atmosphere system. It unfolds not as a single catastrophe, but as a drawn-out adjustment lasting millions of years. The planet, after 1 billion years of restraint, seems to draw a deeper breath and then release it. Oxygen rises within the water column, oxidizing buried organic matter and dissolving long-sequestered reservoirs of reduced carbon. The isotopic composition of the ocean shifts toward lighter values, recording the chemical echo of this massive reaction. The event is not uniform in space or time. Some basins experience the change earlier or more intensely than others, but together they reveal a global transformation. During this interval, the ocean's stratification weakens. Cooler conditions and the gradual breakup of rhydinia increase deep water circulation. For the first time in many hundreds of millions of years, oxygen begins to penetrate farther downward, reaching depths once isolated from the atmosphere. The consequence is a wave of oxidation that sweeps slowly through the deep sea. As it advances, organic matter buried in sediments reacts with the newly available oxygen, releasing carbon dioxide and altering the isotopic balance. Iron and manganese that had remained in reduced form oxidize and precipitate, while sulfide minerals are converted to sulfate. The chemical reorganization of the ocean interior produces new gradients that microbes quickly exploit, transforming ecosystems that have persisted for ages. Some species flourish in the expanding oxygen zones, others retreat to refuges where anoxia endures. The biosphere, though still microbial, begins to change composition in response to this new environmental mosaic. At the same time, the continents experience renewed weathering. As glaciers erode mountain belts left by the assembly of rhydinia, fresh minerals are exposed to air and rain. Chemical reactions on land consume carbon dioxide and deliver sulfate and bicarbonate to the ocean, enhancing both alkalinity and sulfur cycling. The influx of sulfate invigorates bacterial sulfate reduction, generating hydrogen sulfide, that in turn reacts with newly available metals. The balance between oxygen and sulfide becomes delicate, oscillating between brief oxygenation and local euxinia. These redox shifts drive the formation of distinctive mineral assemblages: barite from sulfate saturation, pyrite from sulfide accumulation, hematite from oxidation. Each mineral speaks of an ocean caught between two chemical regimes. The Shura-Monoka event is therefore not a single process, but the intersection of many. Climate fluctuations, tectonic rearrangements, and biological feedbacks all contribute. The isotopic signal captures their combined outcome, a world oxidizing itself from within. The release of carbon dioxide from oxidized organic matter warms the planet slightly, while higher oxygen levels increase weathering efficiency. The feedback loop extends over millions of years, during which carbon isotopes plunge to their lowest values in Earth's history, sometimes more than 10 parts per thousand lighter than the preceding baseline. When the excursion ends, the world emerges more oxidized than before, its surface reservoirs permanently shifted toward higher redox potential. In the ocean's upper layers, these changes reshape life. Oxygen-rich niches expand across continental shelves, supporting more efficient metabolisms and allowing new eukaryotic forms to proliferate. Algae diversify, building the foundation for future food webs. At the same time, deeper waters remain largely anoxic, providing refuges for ancient sulfur-dependent communities. The contrast between surface and deep environments becomes more pronounced, creating ecological gradients that encourage adaptation. Microbes capable of tolerating oxygen gain an advantage, while others evolve to exploit the newly enriched supply of sulfate. The biosphere becomes chemically stratified, with life distributed along a spectrum of oxygen dependence. As this vast oxidation progresses, the sedimentary record captures both destruction and renewal. Old organic-rich deposits are re-exposed and consumed. New carbonates precipitate in shallower waters as increased alkalinity favours their formation. The result is a geological pattern of dissolution and growth erosion and replacement that will later appear as striking unconformities and abrupt isotopic transitions in outcrops across modern deserts and mountains. These rocks, now scattered across continents from Oman to South Australia, preserve the fingerprint of an event that reached every ocean. In them, fine laminations record the gradual loss of reduced carbon and the expansion of oxidized minerals, a transformation written grain by grain. The atmosphere mirrors this change with quiet persistence. Oxygen concentrations, though still far below modern levels, likely rise to several % of present atmospheric proportion. The sky remains pale, but ozone thickens, filtering sunlight more effectively, and perhaps altering the spectral quality of light that reaches the surface. Clouds form from sulfate aerosols generated by oxidized sulfur gases, increasing reflectivity and moderating climate. Weather patterns shift as greenhouse gases decline. Some regions experience cooling, while others retain warmth through local circulation. The Earth remains temperate overall, its climate buffered by the same feedbacks that long ensured stability, yet the chemical identity of its air and water is no longer the same. This oxidation wave leaves an enduring legacy. By transforming reduced sediments into oxidized minerals, it increases the crust's capacity to store oxygen indirectly. Every molecule of carbon or sulfur oxidized and buried as carbonate or sulfate represents a small net addition to the planet's oxidized inventory. Over time, these additions accumulate, gradually tipping the global redox balance toward more oxygenated conditions. The biosphere responds in kind. Photosynthetic organisms facing less sulfide toxicity and more trace metal availability expand in number and diversity. Oxygen becomes a more persistent feature of surface waters, even if it still fluctuates. The atmosphere, coupled tightly to these changes, steadies at a higher baseline. The Shram-Winoka descent is often described as a crisis, but it is also a turning point. The oxidation that drives the negative carbon isotope anomaly consumes ancient organic matter, yet the process clears chemical space for new ecosystems to arise. By burning through the planet's long-stored carbon, the event resets the redox balance and prepares the world for later oxygenation. It marks the transition from the long stillness of mid-Proterozoic chemistry to the restless complexity of the Neo-Proterozoic. In its wake, the planet is left leaner, cleaner, and more reactive, poised for further change. As the isotopic excursion wanes, the ocean stabilizes again, but at a new equilibrium. Oxygen now persists longer in the water column. Sulfate remains abundant. Carbon burial resumes at modest rates. The sky's faint blue deepens slightly. The continents continue to weather under calm rains, and the biological world, though still microbial, begins to show signs of greater energy use. The Shram-Winoka event fades not into silence, but into a higher level of quiet, the calm of a planet that has exhausted one state of balance and found another richer in oxygen and closer to the threshold of the modern world. In the ages that follow the Great Oxidation Descent, Earth enters an era of restlessness unlike any before. The planet has not yet reached stability, but neither has it collapsed into its former anoxia. Instead, it wavers at a fluctuating edge between depletion and renewal, its atmosphere and oceans adjusting to the new balance imposed by the Shram-Winoka transformation. Oxygen no longer lingers merely as a trace gas, but has not yet achieved permanence. It rises and falls in waves, each tied to the rhythms of climate tectonics and the slow evolution of life. The air is faintly stronger enough to alter the chemistry of weathering, to change how nutrients move through rivers and seas, and to push the limits of metabolism in microscopic organisms. The result is a world poised between its ancient past and its approaching future, a world still quiet yet now capable of rapid, if temporary, change. The continents freshly assembled from the debris of Rodinia's breakup lie scattered near the equator, surrounded by wide continental shelves. Rifting has created new seaways that permit circulation between once isolated basins, and through these channels the deep ocean breathes more freely. Upwelling currents carry oxygen into places long deprived of it, while at the same time drawing up ancient nutrients and metals. The biological response is swift. Cyanobacteria and algae bloom across sunlit shallows, increasing organic productivity, and for a time releasing more oxygen to the atmosphere. The skies brighten, fractionally haze thins, and the ocean surface takes on a subtle clarity unseen since the early Proterozoic. For a few million years the planet enjoys another of its transient blue intervals, but now the amplitude of the oscillation is larger, the reach of oxygen deeper. The system breathes more vigorously than it ever has before. Yet the same processes that drive renewal also set the stage for relapse. As oxygen levels rise, weathering on land intensifies, accelerating the oxidation of pyrite and other reduced minerals. This chemical drawdown of oxygen feeds sulfate into the ocean, strengthening microbial sulfate reduction and generating renewed hydrogen sulfide production in deeper waters. The result is another feedback of contradiction. Surface oxygenation encourages deep anoxia. Once again, sulfide accumulates, trace metals are stripped from the water, and productivity in open seas declines. The bright intervals shorten, and the world falls back toward the chemistry of its past. These alternating conditions become the rhythm of the late Proterozoic, the breathing of a planet learning to manage its new oxygen, without yet mastering the balance. Climatic instability amplifies these oscillations. As carbon dioxide fluctuates with volcanic outgassing and silicate weathering, the planet experiences temperature shifts large enough to alter ocean circulation. Periods of global cooling drive the formation of glaciers on highland continents, briefly reducing weathering rates and allowing volcanic carbon dioxide to accumulate. When the ice melts, fresh sediments exposed to rain release nutrients that spark biological blooms and oxygen pulses. The cycle repeats sometimes over tens of millions of years, each phase leaving behind a sedimentary signature of oxidation and retreat. The carbon and sulfur isotopes swing in tandem, tracing the planet's hesitant approach toward modern redox states. In this new dynamic world, life finds both opportunity and challenge. The oxygen fluctuations open windows for innovation. Eukaryotic microorganisms diversify in form and function, some adopting predatory lifestyles, others forming colonies or experimenting with multicellularity. In oxygenated shallows, the higher energy yield of aerobic respiration allows for larger cells and more complex interactions. In anoxic depths, anaerobic lineages persist, maintaining the chemical cycles that underpin the planet's balance. The biosphere becomes stratified not only by light and temperature but by oxygen itself. Each layer of water supports a distinct community, from phototrophs at the surface to sulfate reducers and methanogens below. The ocean becomes a tapestry of microenvironments linked through the slow exchange of elements. On land, the influence of these fluctuations is subtle but real. Chemical weathering under higher oxygen leaves soils faintly more oxidized, rich in iron oxides and sulfates. Rivers carry this chemistry to the sea, sustaining the feedback between continents and oceans. Occasional rises in oxygen permit the formation of thin ozone layers that deepen the sky's blue and shield surface microbes from ultraviolet radiation, These moments allow photosynthetic films and mats to spread farther inland along river margins and lake shores. Although no plants yet exist, these microbial pioneers begin to shape terrestrial landscapes in preparation for future colonization. The interface between rock air and life grows more intricate. The sedimentary record of this time captures the tempo of renewal and regression. In some sequences, thick carbonates alternate with black shales, reflecting shifts from oxygenated to anoxic conditions. Iron-rich bands reappear, testifying to transient oxidation of ferrous iron before its reduction resumes. Sulfate evaporates deposited during arid phases mark times when the global sulfur cycle leaned toward oxidation. Each rock layer is a pulse of the planet's long transition, the evidence of a biosphere oscillating between two stable states. The persistence of these patterns across continents suggests that the fluctuations were not local accidents, but global expressions of a system on the verge of tipping into a new mode. As the atmosphere gains modest oxygen, the greenhouse balance adjusts. Methane, once a major contributor to warmth, becomes less stable in the more oxidizing air, leading to a cooler climate overall. Episodes of glaciation grow more frequent, culminating in the great ice ages of the late Neoproterozoic. These snowball Earth events, when ice may have reached near the equator, temporarily curtail photosynthesis and drive oxygen downward again. Yet their aftermaths bring pulses of weathering and nutrient release that cause renewed oxygen surges. The planet's metabolism grows more erratic, its feedback stronger and more immediate. Oxygen becomes both the agent of catastrophe and the promise of renewal. The chemical dialogue between land and sea intensifies. Oxidative weathering delivers iron and phosphorus that sustain productivity, but also consumes oxygen in the process. Sulfide weathering produces sulfate-fueling deep-sea anoxia. Each interaction forms part of a global circuit that keeps the atmosphere from running away toward either full oxidation or collapse. The Earth's feedbacks remain delicately self-regulating. It is this dynamic equilibrium that makes the planet habitable through instability, allowing life to endure while chemistry shifts. From space, the late Proterozoic Earth would appear slightly brighter and more varied than before. Large ice caps reflect sunlight from the poles. Between them, blue-green oceans stretch across the equator, streaked with zones of high productivity. The air, though still thin by modern measure, shows greater scattering of blue light. The continents, still barren of vegetation, are patterned with oxidized minerals that glow faintly red under the sun. Nothing visible reveals the scale of transformation underway, yet the entire planet vibrates with the tension of approaching change. Within this fluctuating edge of renewal, the stage is being set for a lasting transition. Oxygen no longer acts merely as a reactive trace, but begins to define the energy landscape of the biosphere. The next pulses of glaciation and weathering, driven by tectonics and sunlight, will carry the system beyond oscillation into a new equilibrium. For now, however, the Earth rests between extremes. Its air flickers between clarity and haze, its oceans between blue and green, its life between persistence and possibility. Each breath of oxygen that lingers in the sky lasts a little longer than the one before. The world is not yet changed, but the pattern of change has begun, and in the quiet intervals between redox tides, the planet gathers the strength for the great oxygenation still to come. The final chapters of the Proterozoic unfold in silence that conceals transformation. The Earth, having endured its long cycles of faint oxygen and returning darkness, approaches the threshold of a new breath. The atmosphere, though still thin by modern measure, now carries enough oxygen to alter every boundary of the planet's chemistry. The seas, once wholly sulfidic, begin to clear from their margins inward. The deep ocean remains shadowed, but along the continental shelves oxygen holds its place through the full day and into the night. The biosphere feels this change in its molecular machinery. Enzymes tuned to scarcity find themselves awash in a new abundance, and metabolisms that once hesitated now accelerate. The world's great cycles of carbon, sulfur, and iron continue, yet the equilibrium point has shifted. For the first time since the earliest oxygen rise, the balance between production and loss leans consistently toward gain. It is a quiet victory, an ascent achieved not through eruption but through the cumulative weight of eons. The atmosphere of this time would appear subdued to modern eyes, yet subtly alive. Oxygen may stand at 10% of its present proportion, perhaps less. Yet it suffices to sustain a permanent ozone shield that softens sunlight and deepens the hue of the sky. Clouds drift higher, whiter their microphysics change by aerosols derived from new oxidative chemistry. The horizon loses its persistent haze, revealing longer vistas and sharper contrasts between land and sea. Lightning now ignites small fires, where organic debris collects along dry riverbeds, or in mats of microbial film marking the first appearance of flame as a natural process on Earth. It is a faint symbol of the planet's shift into a new oxidation state energy, moving through air as well as through water. In the oceans, transformation proceeds layer by layer. The upper water column remains the domain of cyanobacteria and algae, now flourishing in oxygen that no longer vanishes each night. Phytoplankton diversify their tiny skeletons, enriching sediments with silica and carbonate. Beneath them, zones of fluctuating redox chemistry become nurseries for new microbial lineages that exploit nitrogen and trace metals more efficiently than before. The expansion of oxygen allows for nitrification, the conversion of ammonia to nitrate, which in turn stabilizes the nitrogen cycle and enhances productivity. Deeper still, anoxia persists, but it recedes with every overturn of water and every increment of burial that locks away reduced carbon and sulfur. The boundary between oxygen and anoxia, once only meters below the surface, sinks by tens, then hundreds of meters. The ocean, while still layered, begins to breathe as a single connected body. Continents reflect this change through their weathering profiles. Soils rich in iron oxides spread across lowlands, painting landscapes in reds and ochres. Rivers carry these oxides toward the sea, where they mix with carbonates and organic matter to form complex sediments. The rise of oxygen accelerates the breakdown of rocks that once resisted erosion, feeding nutrients that sustain the very organisms responsible for atmospheric enrichment. This feedback between life and geology grows tighter than ever before. Each atom of phosphorus liberated from rock fuels photosynthesis that releases oxygen, which then reacts with minerals to create new weathering surfaces. The result is a runaway of mutual reinforcement, a slow-motion acceleration of the planet's oxidative metabolism. Climatic fluctuations remain, but their amplitude begins to lessen. The great glaciations that defined the late Neoproterozoic still come and go, but each episode ends more quickly, as volcanic outgassing and oxidative weathering restore greenhouse gases to the air. The alternation of ice and warmth drives vast exchanges of carbon between reservoirs each cycle, leaving behind distinct isotopic imprints that future ages will read as markers of the Earth's approach toward the modern world. With every thaw, meltwater carries minerals that catalyze biological growth, and with every bloom of photosynthesis, oxygen finds a new foothold in the atmosphere. The air no longer returns to its old faintness. It recovers from each downturn at a higher baseline, climbing in gentle steps toward permanence. Life evolves in concert with these changes. Among the eukaryotes that have lingered for hundreds of millions of years, new strategies appear: colonies that coordinate their growth cells, that differentiate tasks, organisms that glide or float, rather than remain fixed. Oxygen enables energy yields that make such complexity possible. The earliest multicellular forms likely arise in this period, fragile and transient, but heralding an age when biology will begin to shape geology rather than merely endure it. The chemical constraints that once held life to narrow margins now relax, and evolution responds by exploring form and behavior. Every innovation feeds back into the global cycles of matter and energy, amplifying oxygen's hold on the world. The ocean's interior, however, still remembers its anoxic heritage. In deep basins, hydrogen sulfide lingers and reduced sediments continue to accumulate. But the proportion of these basins decreases as continental configurations and ocean circulation evolve. Deep currents, energized by cooling at high latitudes and by the geometry of new ocean basins, carry oxygenated surface water into depths once starved of it. Slowly, iron and manganese deposits thin, replaced by more oxidized sediments. The distinction between the redox worlds, oxygen above anoxia below, softens. By the close of the eon, the deep ocean begins to share in the oxygen that long belonged only to the surface. The isotopic signals of this transformation are unmistakable. Carbon values stabilize near moderate positive levels, reflecting sustained organic burial. Sulfur isotopes show greater fractionation evidence of increased sulfate availability and widespread oxidative weathering. Iron proxies indicate the decline of ferruginous conditions. Collectively, these markers confirm that the planet has crossed a threshold. The oxygen that once flickered now glows steady, and the Earth's crust, ocean and atmosphere together hold a new redox identity. Yet the transition remains incomplete. Oxygen does not yet reach its modern dominance. Instead, the world stands in an intermediate state, no longer the sulfidic realm of the Canfield Ocean, not yet the vibrant oxygen world of the Phanerozoic. It is an age balanced on the edge of transformation. From orbit, such a planet would appear tranquil. The oceans, clearer than in earlier times, reflect a deeper blue, while continents gleam with streaks of iron-rich rock and broad carbonate platforms. Polar regions glint with ice, and the atmosphere, richer in oxygen and ozone, scatters sunlight into more vivid hues. The view offers no sign of the microscopic struggles within, yet the future is implicit in the colour of the seas and the tone of the air. The planet is preparing for the burst of complexity that will soon follow. The threshold of a new breath is not crossed by sudden force, but by accumulation. Each tiny act of photosynthesis, each burial of carbon, each oxidation of rock, adds to the invisible reserve that defines the modern Earth. The Proterozoic ends not with a cataclysm, but with a slow revelation, the realization written in air and water that the planet has at last learned to keep its oxygen. The cycles that once opposed it now sustain it. The next eon will inherit a world transformed, an atmosphere resilient enough to nurture animals, an ocean capable of supporting ecosystems that stretch from shallow reef to deep current. But here at the close of the Proterozoic, the world rests momentarily in equilibrium. Its long struggle for breath nearly won its future, already written in the chemistry of its calm blue air.